Greetings and wishes from Rohini College of Engineering and Technology and myself Manoj, Assistant Professor, Mechanical Department. In this video lecture, we are going to discuss the subject, the heat transfer. So in this part, we are going to discuss the conduction heat transfer and its applications. Heat transfer. As we know that the energy may neither be created nor be destroyed. It can be converted from one form to other. So or else we cannot create or destroy the energy. It can be converted from one form to other. So in case heat is a form of energy that can be transferred from one system to other system is said to be a heat transfer. But without this important word, the sentence is incomplete. That is a temperature difference. Look at the diagrammatic representation given in the slide. If two different systems having different temperature, say the 70 degree and 30 degree is given in the diagram, the heat flow direction is also shown. So according to the second law of thermodynamics, the heat is always flows from higher temperature to the lower temperature. That is the higher energy to the lower energy region according to the second law of thermodynamics. Here it has clearly shown the direction of the heat flow, the 70 degree to 30 degree. Here we have considered the 30 degree as a cold body and 70 degree as a hot body. Therefore, the heat transfer occurs due to its temperature difference between the systems. In the second diagram shown here, the heat is transferred up to the thermal equilibrium occurs between the two systems. So it has been clearly shown the heat is transferred from the higher temperature body to the lower temperature body continuously up to which satisfy the equilibrium condition. If both the body becomes same temperature, at that spot there is no heat transfer taking place. So this has been clearly illustrated in the diagram itself. Therefore, for the heat transfer to happen, the temperature difference is an important one. Without the temperature difference, there is no heat transfer taking place. A thermodynamic analysis is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another. The science with the deals with the determination of the rates such energy transfer is a heat transfer. Heat transfer can be defined as the transmission of energy from one region to another region due to its temperature difference. Modes of heat transfer. The heat transfer taken place by three different modes: conduction, convection, and radiation. But in case all modes of heat transfer require the existence of a temperature difference, as we discussed in the previous slide, the temperature difference is more important for the heat transfer to happen. So in case of all the three modes, conduction, convection, radiation, the heat transfer occurs when there will be a temperature difference. Conduction means a diffusive process wherein molecules transmit their kinetic energy to other molecules by colliding with them. Or else the heat conduction is a mechanism of heat transfer from a region of higher temperature to the region of lower temperature within a medium, whether it is a solid, liquid or gases, or between the different medium in direct physical contact. We can discuss the conduction briefly in the upcoming slides. Convection, simply the heat is transferred from one region to another region, that is the high temperature region to the low temperature region, with the help of any fluid medium or by any fluid medium, whether it is a air or any other liquid or any other gaseous substance. Simply we can say by means of fluids. The heat transfer taking place by any fluid is said to be a convection. Radiation, simply we can say there is no intermittent medium. So without the medium, there is a heat transfer. For example, sun. We are getting the sun's radiation. The sun is out of atmosphere, out of our globe, out of our earth. So in between there is no transmitting medium, even there is a vacuum. Even though we are receiving the heat energy from the sun to the atmosphere, hence it comes as a electromagnetic radiation or electromagnetic, it is in the form of electromagnetic waves. Hence we can say without any medium the heat is transferred from one region to other region is said to be a radiation, as illustrated in the diagram itself. Conduction heat transfer. Conduction is the transfer of energy from one more energetic particle. That means the higher concentration energy. That is the material having higher temperature to the adjacent less energetic. Less energetic in the sense the lesser temperature. So therefore, it happens due to the interaction between the molecules. The diagram at the top shows the direction of heat flow. When any element is exposed to the heat, the conduction taken place immediately due to the molecular interaction. Conduction takes place in solid, liquids or gases. But it is clearly seen that pure conduction is found only in solids. So in case of gases and liquids, the conduction is due to the collision of collision or diffusion of molecules during their random motion. But in solids, it is due to the combination of vibration of the molecules in a lattice space and the energy transport by the free electrons that has been shown in the diagram given below. When one end of the material is exposed to the heat energy or heat, the part which is exposed to the heat getting energized. Due to the vibration of the molecule in a solid body, it hits with the adjacent molecule. Thus, the heat energy is transferred from one molecule to other. Therefore, we can explain the conduction with two different definitions. So, one is the heat is transferred because of the direct physical contact between the different elements. The another one, the heat transfer taking place, otherwise the heat conduction taking place due to the molecular intermolecular vibration or intermolecular transport or conduction of heat energy, right? Here the conduction is based on the principle of Fourier's law, which states that the rate of heat conduction through a plane layer proportional to the temperature difference, or else the rate of heat conduction is proportional to the area measured normal to the direction of heat flow and to the temperature gradient in that direction. Simply we can say like this: the rate of heat conduction, that is Q, the rate of heat conduction is Q, is proportional to the area normal. That means it's which is directly proportional to the area and to the direction of heat flow and to the temperature gradient in that direction. Mathematically, rate of heat conduction Q is equal to Q directly proportional to the area and temperature difference, and which is inversely proportional to its thickness of the layer. That has been shown mathematically. Q conduction is equal to, that means the for the instead of this proportional, we have to add the constant. That means for the conduction heat transfer, the thermal conductivity, the thermal conductivity plays an important role. The thermal conductivity is more important. Every material should have a specific thermal conductivity. According to the thermal conductivity alone, we are deciding whether it is a conductive metal or non-conductive element, right? Therefore, Q conduction is equal to K into A. K is the thermal conductivity, A will be the area, and the temperature difference, the higher temperature minus lower temperature, to the divided by delta X. Delta X is the length or the thickness of the layer. Therefore, Fourier's law states the Q conduction is equal to minus Ka into dt by dx, where dt by dx will be the temperature gradient. That is important. The thermal conductivity. As we mentioned, thermal conductivity is an important parameter in conduction heat transfer, which is defined as the ability of substance to conduct heat. Simply, we can say it is the ability of the substance to conduct heat. Here, it has been shown Q conduction is equal to minus Ka into dt by dx. So, there is a minus sign, the negative sign, which indicates that the heat flows in a direction along which there is a decrease in temperature. So I have to understand this. We have included the negative sign in the Fourier's statement. Q conduction is equal to minus Ka dt by dx, where the negative sign indicates that the heat flow in a direction along which there is a decrease in temperature. As you know that as it is clearly seen in the diagram itself, the temperature T1 is having higher energy, higher temperature, and the heat is transferred through a wall. The temperature T2 is decreased. So therefore, the heat is transferred through any element or a wall, there is a decrement of temperature. Therefore, the negative sign has indicated. In the diagram, it has clearly shown the Q direction, that is the rate of heat flow direction area. Delta X will be the thickness of the layer, and T1 will be the initial temperature and T2 will be the final temperature. General heat conduction equation of Cartesian coordinates. Here we are having three different general heat conduction equation. One is for Cartesian coordinates, another is for cylindrical, and third is for spherical. And here we are going to discuss about the general heat conduction equation of Cartesian coordinates. As illustrated in the diagram, there is a Cartesian, there is a rectangular shaped element having three axes, three directions, x, y, and z. It has been clearly shown, where the dx, dy, and dz is the small area or the smaller elements. So, considering a small rectangular element of sides dx, dy, and dz. Dx and dy and dz or the sides of the rectangular element. Here we are using the first law of thermodynamics. The energy balance of the rectangular element is obtained from the first law of thermodynamics. That is, net heat conducted into the element from all the coordinate direction plus heat generated within the element, which is equal to the heat stored in the element. That is the first law describes. So by deriving all those things, considering the conduction heat transfer, we get the below mentioned equation. That is said to be a general heat conduction equation of Cartesian coordinates. That is dou by dou x of k into dou t by dou x plus dou by dou y into k into dou t divided by dou y plus dou divided by dou z into k into dou t divided by dou z plus q is equal to rho cp dou t by dou t, where the small t represents the time and the capital T represents the temperature. X, Y, Z. There is a three-dimensional Cartesian. That's why it means Cartesian coordinates. It is of three dimensions, where we have X, Y, and Z directions. In this, K will be the thermal conductivity of the material, is given in watts per meter square meter Kelvin, watts per meter Kelvin, and Q will be the rate of energy generated per unit volume, watts per meter cube, and rho will be the density, C will be the specific heat capacity of the element. When we are considering the general conduction equation for the Cartesian coordinates as one-dimensional and steady state in a plane wall. So when we are considering it as a one-dimensional, dt by dy and dt by dz becomes 0 since it is one-dimensional. And in case of one-dimensional and steady-state heat conduction through a wall, plane wall, of uniform conductivity without the heat generation, therefore Q value also be 0. Steady, that the steady represents dt divided by dt. There is a time dependent. The steady represents the time dependent. That is, the time dependent variable becomes 0. The remaining, therefore, the general heat conduction equation becomes d square T divided by dx square is equal to 0. In the next part, we can discuss the electrical analogy of heat conduction. Thank you.